Hello, students, and welcome. Today, we are going to explore a very fundamental question. What is everything around us made of? I mean, what are the smallest, most basic building blocks of all matter? We're going to dive into the world of atoms and unlock some of matter's biggest secrets.
So, let's take a quick look at what we'll be covering today. We will begin with a chemical mystery that puzzled early scientists. Then, we will properly meet the atom itself. After that, we'll learn the special language scientists use for elements, figure out how they even managed to weigh an atom, and finally, we'll look at John Dalton's brilliant explanation that tied it all together.
All right, to really understand atoms, we need to start with a bit of a puzzle, a mystery that scientists faced a long time ago. To solve it, we need to revisit two very important laws that you may have studied already. These are the laws of chemical combination.
Now, you might remember these two laws. On one side, we have the law of conservation of mass. This simply means that in any chemical reaction, nothing is lost. The total weight of what you start with is exactly what you end up with. On the other side is the law of constant proportions. This law tells us that a chemical compound is like a fixed recipe. Take water, for example. It is always made of the same fixed proportion of hydrogen and oxygen. These laws showed scientists that chemical reactions are not random. They follow very strict rules.
So, these laws, they were like important clues, and they led scientists to ask a very, very big question. Why? Why do these rules exist? What is actually happening at a deeper level that forces chemicals to always combine in these same fixed ways? There had to be an underlying reason.
And the answer to that big question, well, it lies in a single, incredibly tiny particle. And that particle, students, is the atom.
The easiest way to think about it is this. Just like a large building is made up of many individual bricks, everything around us, all matter, is made up of atoms. The desk you're sitting at, the air you are breathing, even you are all made of countless atoms.
Now, a very logical question comes to mind. If everything is made of atoms, why can't we just see them? That's a very good question.
Well, the reason is simply because they are unbelievably small. So small, in fact, that our usual units like centimeters or millimeters are just too big to measure them. We need a special, much smaller unit called the nanometer. And to give you an idea of how small a nanometer is, there are 1 billion nanometers in just 1 meter. That's a 1 followed by 9 zeros.
And even though our naked eyes can't see them, with our modern technology, we actually can get images of them. Look at this. This isn't a drawing, it's a magnified image of the surface of silicon. Each of those little bumps that you see is an individual atom. It's quite amazing, isn't it?
Okay, so scientists are studying all these different types of atoms, which we call elements. Now, imagine having to write out the full name, hydrogen, aluminum, carbon, every single time in your notes. It would be very tedious. So they needed a shorthand.
And that shorthand is what we call an atomic symbol. A scientist named Berzelius came up with this simple idea. Let's just use 1 or 2 letters from the element's name. This system was so good that it was officially approved by the IUPAC, which is the main organization for chemistry, and it's now used by scientists all over the world.
Now, there is a very strict rule for writing these symbols that you must remember. The first letter is always a capital letter, and if there is a second letter, it is always a small letter. For example, aluminium is A capital L small, not 2 capital letters. This is so important because, look at the last example, C capital and O small is the element cobalt. But if you write both letters as capitals, CO, that's not cobalt at all. That's carbon monoxide, a completely different chemical compound. So please be very careful with this rule.
Now, sometimes you'll see a symbol that doesn't seem to match the English name. For example, why is iron Fe? This is because some symbols come from the element's name in an older language, like Latin. The Latin word for iron is ferrum, and that's where we get Fe. The same goes for sodium, Na, which comes from natrium.
All right, so we can name them and we have symbols for them. But the next big challenge for scientists was, how do you weigh one? How do you find the mass of something that's so incredibly tiny?
Think about it. It's an impossible task, right? You can't see an atom, you can't hold it, so you definitely can't put it on any weighing machine. So scientists had to be very clever. They decided that instead of finding the actual mass, they would find its relative mass by comparing it to another atom.
Let's use an analogy to understand this. Imagine a fruit seller who doesn't have any standard weights, like 1 kilogram or 2 kilogram weights. So he picks up a watermelon and just decides, okay, I will call the mass of this watermelon 12 units. Then he cuts that watermelon into 12 perfectly equal pieces. So what is the mass of one piece? It's 1 unit, right? Now he can weigh any other fruit by comparing it to these pieces. This is exactly what scientists did with atoms.
So in chemistry, our watermelon is a specific atom, carbon-12. Scientists decided to use it as the standard. And the one piece of watermelon is called the atomic mass unit, which we write as a small u. By definition, one atomic mass unit is exactly 1/12 of the mass of a single carbon-12 atom. This became the standard unit to measure the relative mass of all other atoms.
So let's recap. We have the idea of atoms, we have symbols for them, and we have a way to compare their masses. Now we come to a very important scientist, an English chemist named John Dalton. He was the one who put all of these ideas together into the first proper scientific theory about atoms.
This is John Dalton, and his great achievement was to show how the existence of atoms perfectly explained those two laws we started with, the law of conservation of mass and the law of constant proportions.
Dalton's theory was based on a few main points, or postulates. He said that all matter is made of atoms, that these atoms are indivisible and can't be created or destroyed. He also said that atoms of one element are all identical, but are different from the atoms of other elements. And finally, he proposed that atoms combine in simple whole number ratios to form compounds.
Now let's see how his theory explained those laws. Look at his second point. Atoms cannot be created or destroyed. Now think, if a chemical reaction is just a rearrangement of these atoms, then it makes perfect sense that the total mass before and after the reaction must be the same. Nothing new is created, nothing is lost. This beautifully explains the law of conservation of mass.
And what about the second law? Look at points 5 and 6. Dalton said that atoms combine in simple whole number ratios, and that for any given compound, this ratio is always the same. So for water, it's always 2 atoms of hydrogen with 1 atom of oxygen. Always. This fixed recipe is why a compound always has the same proportions of elements by mass. And there you have it, an explanation for the law of definite proportions.
And with that, students, you now have the fundamental keys to understanding chemistry. This idea of the atom, it really is the foundation for everything else that we are going to study. Once you understand the atom, you can begin to understand all of chemistry.
So we've understood what atoms are, but this leads to the next question, doesn't it? We know atoms rarely exist on their own. So how do these atoms actually join together? How do they form all the different things we see around us? That is exactly what we will explore in our upcoming topics, when we learn about molecules, ions, and chemical bonds.